Hello, everyone. Thank you for the introduction. So indeed, my name is Pierre Palud. I'm a second-year PhD student. And indeed, today I'm going to talk about the inference of physical conditions in star-forming regions using a new Bayesian paradigm and a spatial regularization. So in a nutshell, the whole point of my presentation is going to be to derive new tools to better understand the effect of radiative feedback on a parent cloud. To do so, the tools that I'm going to derive perform efficient estimation of physical conditions in star-forming regions. So here are, for instance, two such star-forming regions, the Carina Nebula and the Pillars of Creation taken by the James Webb Spatial Telescope. And here is a third such image, the Orion B cloud. The Orion B cloud, this picture on the right, was taken with a large survey by the Orion B consortium, led by Jérôme Petit and Marie Van Guerin. And this picture here, just as an indication, the moon represents the scale onto the projection onto the celestial sphere. This image is a very rich data set. It contains around 1 million pixels and covers 100 square parsecs. So this cloud is very well resolved, spatially. It is also very well resolved spectrally with hundreds of thousands of spectral canals, including tens of lines. The main challenge with this data set is actually the great variations of signal-to-noise ratio in the observations, both spatially and spectrally. Why is that a problem? Well, the overestimation procedure that one relies on in order to reconstruct physical parameters, such as, for instance, the temperature, the intensity of the radiative field G naught, or whatever, this estimation procedure relies on a physical model or a grid of physical models, which predicts observations. These predicted observations are then compared with actual observations using a function like the likelihood or a least square function. And this comparison is used to update the reconstruction of the physical parameters. And this process is iterated until the predicted observations are close enough to the actual observations. This procedure is fundamentally pixel-wise, meaning the operation is done pixel by pixel. Here is, for instance, an application on the Carina Nebula. This observation map was taken with the Herschel Spatial Telescope, and it's a map of around 200 pixels. If we look pixel by pixel, the model on the right in blue reconstructs very well the observations in purple. However, if we look at the reconstruction map as a whole, we find that there's absolutely no spatial consistency. The reason is that in the low SNR regime, there are a lot of combinations of parameters that reconstruct equally well the parameters. So the reconstruction that we obtain with this kind of method, pixel-wise, doesn't enable to perform scientific analysis on the reconstructions. We, in order to perform better estimations, use a spatial regularization that is going to help drive the reconstructions towards meaningful regions in the low SNR regime. We are also going to use a Bayesian framework in order to provide uncertainty quantifications with credibility intervals, and the tools that we derived are actually fast. The method that we derived is, I'm going to first show it evaluated on a synthetic PDR map and then to an actual observation. So who says synthetic PDR map says PDR. Photodissociation region, I'm going to introduce it in a very few words because most of you already know what it is. Photodissociation region basically is a region of the interstellar medium illuminated by a type O or type B young star. The chemistry and the physics of the photodissociation region is mainly controlled by the photons emitted by that star. We're going to describe such a region with three parameters, essentially. First, the G naught, the parameter that quantifies the intensity of the incoming radiative field emitted by the star. We're going to assume that the photodissociation region has a constant thermal pressure, denoted PTH, and that it has a total visual extinction AV. Such a cloud can be simulated using the Meudon PDR code, for instance. So again, three parameters to fully describe the cloud. And from these three parameters, the Meudon PDR code iteratively solves a large set of partial differential equations involving thermal balance equations, radiative transfer, and a large network of chemistry. Its outputs, its predictions, are integrated intensity of a few lines. I said we're going to evaluate the method on a synthetic PDR map. So here is the map. It is divided in 3 regions. In the extreme right, we have an edge-on PDR. So you can imagine that on the right of the image, there's a star or cluster of stars. So the PDR is actually seen edge-on. And then further to the left, we have a dark cloud with a buried source in it. So here you have the true maps that we are going to try to reconstruct of the parameters, thermal pressure, the G naught, and visual extinction. From these parameters, from these maps of parameters, using the Meudon PDR code and a noise model, we generate inertial lag observations. So we use mid-J CO lines, 10 of them. And from these lines only, we try to reconstruct the maps of the parameters. Here, I only show on the right the reconstruction that we obtain with the classic method, the G naught. And we can see again that these maps has no spatial consistency, that it doesn't enable to perform scientific analysis, while the method that we propose yields this kind of reconstruction, which is much better. So from now on, I'm going to try to describe to you how we reach such good reconstructions. So as I said, we use a Bayesian approach. A Bayesian approach, basically, it allows to perform inferences, providing credibility intervals. So it actually gives a more complete description of the parameter space. So instead of minimizing a cost function, we consider an a posteriori probability distribution of the parameters given the observations. This probability distribution is the product of 2 terms, a likelihood term that quantifies how well the parameters reconstruct the observations, and a spatial prior that orients the reconstructions towards smooth maps. This a posteriori distribution is actually a complex distribution, so we can't extract estimators from it as is. So we sample from it, obtaining histograms using a Markov chain Monte Carlo algorithm. So our overall method contains 3 ingredients: a likelihood function, a spatial prior, and a MCMC algorithm. I'm going to detail quickly 3 of them. The likelihood function relies actually on an observation model that is here on the top left. So there are 2 cases. If a line is detected, then the observation is actually deteriorated with a mixture of noises, a multiplicative noise that corresponds to a calibration error while performing the observation, and an additive noise that comes from thermal noise in the instruments. And when the line is not detected, we simply have access to a telescope detectability upper limit. This observation model comes with 2 practical difficulties. The first one is the fact that we rely on the Meudon PDR code, which is a very expensive numerical code. So we approximate it, for instance, with a neural network in order to be much more computationally efficient. The second main issue is the mixture of both additive and multiplicative noise. This mixture is dealt with an approximation of the likelihood. And you can notice, for instance, that when the predicted intensity is low, then the additive noise dominates. And on the contrary, when this intensity predicted is very high, then the additive noise is neglectable, which means that at low SNR regimes, we're going to use an additive model approximation. And at the high SNR regimes, we're going to use a multiplicative model. And at intermediate values, we're going to use a mixture of them. So this is for the likelihood. The spatial regularization that we use, that's going to orient towards smooth map, represents the image as a lattice. Each pixel corresponds to a node of the lattice. And we consider that each node contains a few neighbors, 4 of them. And what we're going to enforce is that a node has to be close to the average of its neighbors. This is some kind of adaptive stacking. Adaptive because at high SNR regimes, the regularization is going to be neglectable in weight compared to the likelihood. And in the low SNR regimes, then the regularization is going to drive the reconstructions. So for instance, here on this map, we can see that this is really not smooth. So it's going to be considered as very unlikely. Here, for instance, we see that this pixel is very far from the average of its neighbors. while the reconstructions that we obtain are much smoother, so they have a low penalty, and you can see that each pixel is very close to the average of its neighbors. So now that we have the likelihood and the regularization, we actually have access to, we fully define the posterior distribution. So now we only have to sample from it. And for that, we rely on a Markov chain Monte Carlo algorithm. I'm just going to describe it in a few words, using a Gaussian mixture. So this is just a very toy example. So you could imagine that in some region of the sky, we have some molecular cloud, we have this kind of figure for the thermal pressure and the G0, and all these modes are likely environments that recreate well the observations. To explore all of the modes, we rely on two operators. The first one is a fast local explorator. It explores efficiently one mode. So for instance, for this mode, it understands that the thermal pressure is not well constrained. So it takes large steps in this direction, while the G0 is well constrained. So it takes small steps in this direction. The other operator that we use allows to jump from one mode to another, to identify all the likely zones. So here, for instance, it generates a lot of candidates and chooses one with a high score. So this is what it gives in practice. So on the left here, what I'm showing is the Monte Carlo, the Markov chain Monte Carlo in real time. So I show the first 150 iterations and then the last 150 iterations. That's what you have a jump at some points. And you can see that it reconstructs very well one mode, but only one mode. While if we perform only mode identification, we manage to jump from one mode to another, but we only do that and we don't efficiently explore the local modes. So what we propose is to combine both of the operators to efficiently reconstruct all the modes. With this, once this method, now that the full method is described, we can understand now where the better reconstruction of the G0 comes from. And if we look at the whole reconstructions, the first column shows the true values that we started with. And the second column shows the results with the classic method. So once again, not usable, not exploitable for physics. The third column represents the results we obtained with our proposed method. So much better, much smoother. And the last column shows the credibility intervals that come along with the proposed estimator. Really quickly, I'm going to show you an application to real data. So a less exciting, technically exciting example. So one pixel only. It's going to be the NGC 7023 PDR. So it's one of the closest PDR, and it's one of the most studied. It has a edge-on geometry. And very interestingly, it has previous estimations in the literature of parameters that we want to reconstruct. So this is the kind of results that we obtain. As I mentioned, we go construct an histogram. So what is very interesting is that the value from the literature falls exactly in a mode that the code identifies, but our algorithm also identifies a second very likely mode that reconstructs well the observations. And if we look at how well the algorithm reconstructs the observations, well, we can see here that all the lines, orange stands for the reconstruction by the model, and blue stands for the observation with the noise that come with it. And you can see that the reconstructions are always very close to the observations, which means that the two modes reconstruct very well the observations. To conclude, we derived a new tool that is now ready to be used, and that is going to be soon available on the Observatory of Paris website. It relies on two main ingredients: a spatial regularization that orients the reconstructions towards smooth maps, and a Bayesian approach that provides both estimates of the parameters along with the corresponding credibility intervals. We applied, I showed applications to a 4,000 pixels case and to a 1 pixel case, a real one. We are currently working with real data, with the horse head and some other maps, and future applications include the James Webb Spatial Telescope observations. Thank you for your attention.